Bismillahirrahmanirrahim. Assalamu alaikum. How are you, students? I hope everyone will be fine. And today our course of discussion is Analytical Chemistry, and course code is CAM2112. The topic that we are going to discuss is complexometric titrations. In today's lecture, that is about complexometric titrations. We will talk about first we will talk about Kelown effect and then we will talk about complexes and their formation constant, and next is about complexation equilibria, in which we will discuss the equilibrium of EDTA, in which many steps are involved for the dissociation and formation. And the next is about formation constant of calcium and EDTA complex. And finally, we will discuss about metal EDTA titration curves. Ethylene diamine tetraacetic acid, that is also known as EDTA. We can represent it by symbol H4Y. It can be denoted by H4Y. So EDTA is a tetraprotic acid, and hydrogens in case of H4Y, we can say that it is tetraprotic acid, and the hydrogen in H4Y refers to the 4 ionizable hydrogens belonging to the 4 carboxylic acid groups. 4 hydrogen ions come from 4 carboxylic acid groups. So at sufficiently low pH, the nitrogens can also be protonated, and this protonated EDTA can be considered as hexaprotic acid. Then there will be 4 ionizable hydrogen ions that will be from 4 carboxylic groups, and then it will be tetraprotic. And if it has at a low pH, sometimes nitrogen can also be protonated, and this protonated EDTA can act as a hexaprotic acid. However, this occurs at very low pH, and EDTA is almost never used under such conditions or under low pH conditions. So it is unprotonated ligands Y4 negative that form complexes with metal ions. That is, the protons are displaced by metal ions upon complexation. So next is a Kelown effect, or we can say that Kelown effect is when more complexing or chelating groups are present, then it is much better and we can get stable complex. So multidentate chelating agents form stronger complexes with metal ions than if we compare it with the bidentate or monodentate ligands. So this is due to a result of thermodynamic effects in complex formation. As we know that chemical reactions are mostly driven by decreasing enthalpy, that is liberation of heat, that could be denoted by negative delta H. And by increasing, and these reactions are driven by increasing entropy, like increased entropy mean that is increased disorder, that is denoted by positive delta S. So chemical process is spontaneous when free energy change delta G is negative. So we can represent is this delta G is equal to delta H. Delta H is enthalpy minus T delta S, that is change in entropy. So the enthalpy change for ligands with similar groups is often similar. For example, 4 ammonia molecules that are complexed to copper 2 positive ions and to 4 amino groups. These 4 amino groups are formed from 2 ethylene diamine molecules complex to copper 2 positive, which results in about the same release of heat. We take 2 examples. The metal is the same, that is copper 2 positive, and this copper 4 positive will bind to 4 ammonia molecules, and the other copper 2 positive will bind to 4 amino groups from 2 ethylenediamine molecules. So the release of heat for both will be same. However, more disorder or entropy is created by the dissociation of copper tetramine complex, in which 5 species are formed, than in dissociation of copper EDTA complex. So in case of copper tetramine complex, 5 species are formed in case of dissociation. So more disorder or entropy is created. But in case of copper EDTA complex, 3 species are formed in case of dissociation. So the delta S is greater for copper tetramine complex, and it will create more negative delta G and greater tendency for the dissociation. So multidentate complexes are more stable. They have higher, larger Kf values. They have larger formation constants because of the large entropy effect. So this is known as Kelown Effect or Chelate Effect, and it is pronounced for chelating agents like EDTA, which have many ligands, which have more ligand atoms to occupy up to 6 coordination sites on the metal ions, or 4 coordination sites on the metal ions. So the complex that EDT will form will be more stable as compared to complex that is formed with the monodentate ligand or bidentate ligands. So complexes play a vital role in many chemical and biochemical processes. For example, in case of blood, heme molecule in blood holds iron tightly because the nitrogen atoms of heme form strong complexing bonds. So in general, nitrogen atom that is derived from an amino group is a good donor atom, or it is a good complexing agent. So iron, in case of iron 2, in turn bonds quickly with oxygen to transport oxygen gas from the lungs to elsewhere in the body, and then easily releases it because oxygen is a poor donor atom or complexer. So in case of carbon monoxide, it can kills uh, the cells because it is strong complexing agent. It can displace oxygen, and it can bind to heme 200 times more strongly than thus oxygen can bind. So it can form carboxylic hemoglobin that is dangerous because it removes oxygen from that uh, blood. So many cations will form complexes in solution with different substances that have a pair of unshared electrons, and we like oxygen on sulfur atom, oxygen atom, or nitrogen atom in the molecules that are capable of satisfying the coordination number of the metal cations because these are electron rich species. So metal cation is Lewis acid. We already discussed about it. That is an electron pair acceptor, and complexer is our ligand is a Lewis base. That is electron pair donor. So the number of molecules of the complexing agent that are called ligands that depends on the coordination number of metal cations and on the number of complexing groups on that ligand molecule. So in this case, ammonia is simple complexing agent or ligand with one pair of unshared electrons that will complex with the copper ions. Like in this equation, you can see that copper 2 positive are complex with the 4 ammonia molecules, and in ammonia, each nitrogen atom can give one electron pair. In one ammonia molecule, one nitrogen atom can give pair of electron. So the 4 ammonia molecule will bind with that copper metal ion. So hence the copper ion acts as a Lewis acid and ammonia as here as a Lewis base. So the copper 2 plus ion is a pale blue in solution if it is in hydrated form, while ammonia that is amine complex is a deep blue. So similar reaction can occur with a green hydrated nickel ion to form that can form a deep blue amine complex. So ammonia can also complex with the silver ions to form a colorless complex, and the two ammonia molecules complex with each silver ion in a stepwise fashion, in stepwise manner, and we can write an equilibrium constant for each step, and that equilibrium constant is also known as formation constant, and it is denoted by Kf. So here we will take the example of complex of ammonia and silver. So here in this first equation we can see that silver silver plus react with one ammonia molecule, and it can form silver ammonia complex, and we can write its formation constant product over reactants. So this formation constant for silver and one ammonia molecule will be 2.5 10 raised to power 3, and then this will further react with another ammonia molecule, and it will form formation constant will be Kf2 for second step, and again it will be reactant over products divided by reactants, and the formation constant is value is 1 10 raised to power 4 for ammonia silver complex. So overall reaction is a sum of two steps, and overall formation constant is the product of stepwise formation constant. Like we can say that overall formation constant is Kf is equal to product of formation constant 1, that is for step 1, that is Kf1, multiplied by formation constant of second step, that is Kf2. So we will multiply these two constant value, and we will get equation that is equation 3, and that is overall formation constant will be 2.5 10 raised to power 7. So the formation for the formation of simple 1-1 complex, for example one metal and one ligand, the formation constant is simply Kf, that is we can say ml divided by m into L. So formation constant is also called as stability constant, and that is represented by Ks. So this reaction is reversible, like as we consider formation constant, then if we reverse the reaction is reversed, and we can write this equilibrium in opposite direction, as that is known as dissociation. So if we do this, the concentration terms are inverted in the equilibrium constant expressions, and the equilibrium constant then are simply the reciprocals of formation constants, and they are called as instability constant, that is denoted by Ki, or dissociation constant, or that is represented by Kd. So this Kd is equal to 1 over Kf, that is uh, inverse of that formation constant. So if we consider that the silver is combined with two ammonia molecules, then it will dissociate into silver positive ions and two ammonia molecules. Then the right side we will write in above equation, and then it will be divided by the left side. So the value will be 4 10 raised to power minus 8, and so complexation equilibrium of metal and ligand that form complex, we can denote their reaction by different steps, and many metals form complex coordination compounds more than that have several ligands. So this complexation reaction could be in stepwise manner. So we can write it like this: if M is a metal and there is one ligand, then it will form Ml, and we can denote its formation constant by K1. So if there is another ligand and that is bind to this Ml, first metal ligand complex, then it will form Ml2 and formation constant for this will be K2. Similarly, this Ml2 further react with another ligand and it will form Ml3 type, and this formation constant will be K3. And similarly, if there are number of there are different metal ligand complex, they further combine with different ligands, then we can write it Ml n. N could be any number greater than 1, 2, 3, 4. It goes up to 6 or 8. So we will denote it by Kn. So multiple steps of these reactions can be combined by using these overall formation constants. So we will denote it by beta. So overall ligands and metal ions and overall ligands which are present, we will combine them and it will be denoted by beta, that is overall formation constant. So we will we will represent ETTA as it has 4 K values corresponding to stepwise dissociation of 4 protons. For example, in first equation we can see that H4Y, first we consider it as tetraprotic acid, so it will dissociate into H positive ion and H3Y negative ion. So at its Ka value will be 1 10 raised to power minus 2, and here its formation constant, we can write it as a product over concentration of reactant. So H positive and H3 Y negative product of these two, and they divided by, we will write reactants, that is H4Y. So in next equation, then we have three protons with EBT. So H3Y, this will dissociate into another it will dissociate another H positive one, and it will remaining will be H2Y2 negative. So two protons from carboxylic acid are displaced, are dissociated. So this will be Ka2 and value is 2.2 10 raised to power minus 3, and we can write here H positive into H2Y2 negative divided by H3Y negative. So third equation is here two protons are left at ADTA, two are protonated and two are disprotonated. So two are displaced, two hydrogen ions are displaced. So here again one hydrogen ion will be replaced and it will form HY3 negative ion. So this will be Ka3 and its value is 6.9 10 raised to power minus 3, and its product will be H positive into Hy3 negative divided by H2Y2 negative, that is reactant, that is initial stage. So Hy3 is the final, that where one hydrogen ion is left and it will dissociate into H positive, and we will get Y4 negative, and all carboxylic acid groups from all carboxylic acid groups protons are dissociated. So this will be as Ka4 and the value will be 5.5 10 raised to power minus 11, and this Ka4 is equal to H positive into Y4 negative and reactant is HY3 negative. So in when we are to predict the completeness of reaction like complexation, then we need to count all equilibrium that are involved in metal and ligand complexation or formation. So often specify conditions for a given system can give conditional formation constants. So conditional formation constant for ETTA are represented by Ka, and we will discuss it about with different steps, that step by step, and its predominant forms mostly depend on pH. Ethylene diamine, tetraacetic acid, that is also known as EDTA, We can represent it by symbol H4Y. It can be denoted by H4Y. So EDTA is a tetraprotic acid and hydrogens in case of H4Y. We can say that it is tetraprotic acid and the hydrogen in H4Y refers to the four ionizable hydrogens belonging to the four carboxylic acid groups. Four hydrogen ions come from four carboxylic acid groups. So at sufficiently low pH, the nitrogens can also be protonated, and this protonated EDTA can be considered as hexaprotic acid. Then there will be four ionizable hydrogen ions that will be from four carboxylic groups, and then it will be tetraprotic. And if it has at a low pH, sometimes nitrogen can also be protonated, and this protonated EDTA can act as a hexaprotic acid. However, this occurs at very low pH, and EDTA is almost never used under such conditions or under low pH conditions. So it is unprotonated ligands Y4 negative that form complexes with metal ions. That is, the protons are displaced by metal ions upon complexation. So in this figure, we can see that it illustrates the fraction of each form of EDTA as a function of pH. pH is on the x-axis and fraction of each form of EDTA is on the y-axis. So since the anion Y4 negative is a ligand species in complex formation, the complexation equilibria are affected mostly by pH. So H4Y has a very low solubility in water, and so the disodium salt Na2H2Y that has two water molecules is generally used, in which two of the acid groups are neutralized. So this salt will dissociate in solution to give H2 Y2 negative ions, and the pH of solution will be at this point will be approximately 4 to 5. Here you can see in this figure that H2 Y2 negative is when salt dissociate, it will dissociate at pH 4 to 5, and we can get Y4 negative at about between pH 10 to 12. In this slide, you can see a ladder diagram which shows the distribution of EDTA species at different pH. So this ladder diagram was actually contributed by Professor Galina Talanova, that was from Harvard University. And as we see in previous slide that nitrogen on EDTA can protonate in very acidic solution. So, and when we consider this, we can write this 6 Ka values if also nitrogen is involved in that. So, in that case, we can say that pK3 to pK6 values in this ladder diagram corresponds to values of Ka1 to Ka4 that in equations we described in previous slide. From that equation we can say that these values from pk36 pk3 to pk6, that pk3 is h3y minus, at which ph is about 2, and pk4 is about h2y2 negative, and pH here is pH is pKa4 is equal to 2.66, and the next pK5 is H3 negative, and here pH pK value is 6.16, and pK6 where all protons are dissociated are then it will be Y4 negative, and pH or pK value will be 10.24, as we already see in this previous slide. So from pK3 to pK6 values that correspond to Ka1 to Ka4. That is dissociation of EDTA one proton from one proton to four protons from carboxylate groups. So you can see that protonated nitrogens occur around pH 0 to 1.5, that is pK1 and pK2. At this pH, the nitrogen can be protonated, and this can occur at pH 0 and pH 1.5. So above there is a higher monobasic, and in the lower values are lower monoacidic values. So pH will be increased in the above, and it will decrease in the lower values. So dominating species in dissociation of EDTA will be Y4 negative, that may occur at pH 10.24. Formation constant for EDTA and calcium complex, chelate complex, could be represented by equation. It is similar like we discussed in previous slides, and here we will consider the formation of EDTA chelate of calcium 2 positive ion, and we can write it as calcium 2 positive ion, and they will react with a Y4 negative, uh, and they will form calcium Y2 negative complex. So the formation constant for this will be Kf will be equal to that Ca2 negative on the right side will be above, and then below we will write the product of calcium 2 positive and Y4 negative, that we can say these are reactants. So we can describe formation constant of EDT complex with a metal ion in this way, and the dissociation constant will be reverse of this, like we described in our previous slides for EDTA. So EDTA titration curves are similar to we here in this figure. In this curve, we will assume it as same as strong acid and strong base curve. Like in strong acid and strong base, we use sodium hydroxide. For example, we take the example of sodium hydroxide and HCl. Then we can get the curve like this. So in case of EDTA titration curve, the volume will be taken on x-axis, that is the volume of EDTA that is added, and on y-axis there will be concentration of metal ions that we can determine, and EDT, and we assume that EDT and metal reacts completely and instantly here, then we can get equivalence point between this at about between 8 to 10, and we can say that this equivalence point will be that point where the equal moles of EDTA and equal moles of metal ions contribute equally. So at this point they will form stable complex, and in starting point we can see that as we increase the amount of EDTA, and at one point the reaction will be completed, and after that the region you can see the region 1 is excess metal ions present here. Region and 2 is that region where is equivalence point equal number of EDTA and metal ions are present, and region 3 is that EDTA is in excess here. So metal EDTA titration curves. Here we will take example of calcium chelation with EDTA. As we know that titration is performed by adding the chelating agent to the sample, and here sample is a metal solution. So reaction may occur, and titration curve for calcium, that is here we can see in figure that this is titration curve for calcium 2 positive ion that is titrated with EDTA and at pH 10. So before the equivalence point when both calcium and EDTA react equally, So before this equivalence point, the calcium to positive ion concentration is nearly equal to the amount of unchelated or unreacted calcium. Since the dissociation of chelate is slight, that is analogous to the amount of an unprecipitated ion. So at the equivalence point and beyond, pKa is determined and from the dissociation of chelate at given pH. So the effect of pH on titration is apparent from the curve. Here you can see in this figure. And for titration, it is at calcium pH, the curve, this will be at pH 7. You can see curve, and at pH 10, you can also see the curve. And we can find out concentration of metal ions.